So I'm going to go over some principles of the adaptive immune system, but I'm not going to really talk in much detail about them because you'll learn about them in the coming lectures. So, antigens, which are things that stimulate the immune system, so pieces of pathogens that stimulate immune responses, will interact with antigen receptors on innate immune cells and lymphocytes, and that's how the innate immune system is going to talk to the adaptive immune system. And that's a very intricate process, which you'll hear about in a few lectures. The main components of adaptive immunity that offer you protection are antibodies and T cells. And we'll talk about how antibodies mostly deal with things that are extracellular, and T cells have to find a way to kill pathogens that are inside of cells. How do they know and how do they recognize a pathogen? Antibodies and T cell receptors, we each have millions of them, and each one has a different specificity to recognize a different piece of a different pathogen. And our body has a very elegant way of creating all of this diversity, and that comes from the genes that are going to be recombined in multiple different ways to give you that diversity. And again, you'll learn a lot more about that in coming lectures. So, once the adaptive immune cells are activated, then they can start to make clones of themselves so that each cell that's a clone recognizes only one antigen, and that's all it will ever recognize. But it can make many, many copies of itself and go out and fight that particular infection. But that clone is only good for fighting one infection in your body. It won't be good for fighting any other infection in your body. Now, sometimes our adaptive immune cells can make receptors that could recognize self-proteins. Now, of course, we don't want that, so we only want them to recognize foreigners, so usually they're eliminated, but unfortunately, not always. Remember again, lymphocytes start off in the bone marrow because all of our cells from our immune system start off in the bone marrow. But they're eventually going to move to other lymphoid organs, which you'll learn about, including the thymus and lymph nodes and the spleen. So lymphocytes get activated in lymphoid organs. They're not out at those barrier sites. They're not at those areas where an infection is first occurring. And that's why they don't know that the infection's occurring unless the innate immune response tells them. And that's by innate immune cells actually picking up pathogens and going to a lymphoid organ to alert the adaptive immune system. Now again, mucosal surfaces have a specialized and slightly different way of responding to pathogens, and you'll also learn about that later on in the lecture series. And again, the main benefit of your adaptive immune response is immunologic memory. Learning after seeing a pathogen for the first time so the body can make a quick and strong response the second time so you don't get sick. All right, so again, just a reminder, lymphocytes, all immune cells, start life in bone marrow. And then you have lymph nodes throughout your body, you have your spleen, you have your thymus. All of those organs you're going to learn about in the next lecture, and they all take part in cell development, educating cells, being a home for cells, being a site of initiating adaptive immune responses. Okay, so overall, effector mechanisms of immunity. So effector mechanisms are sort of once the immune system's alerted, what does it actually do? How does it have an effect on the infection? Now, of course, first, the innate immune response has an effect. It can kill pathogens. It can eliminate some of those pathogens. Then it alerts the adaptive immune response, and you get antibodies and T cells that can help to kill pathogens. Now, another thing that can happen with your immune system is that it malfunctions. It doesn't always work right. Sometimes that's from a genetic defect. Sometimes that can be from an infection. So you can have inherited or acquired defects in your immune system. And actually, those defects and those problems, if we understand what goes wrong with those problems, it teaches us a lot about how the immune system works. So, speaking of problems with your immune system, when it isn't working correctly, you can have things like allergies or autoimmune disease or rejection of a transplanted organ, and all of that is related to what your adaptive immune system is doing. It's not usually ever related to what your innate immune system is doing. And of course, one of the most important things we've been able to do once learning more about the immune response is to develop vaccines that can stimulate an immune response and stimulate a memory response without you ever being sick, so that you never have to get sick. So I just want to briefly touch on some of the adaptive immune system functions, but you'll learn about these in much more detail in coming lectures. So antibodies. Antibodies work outside of the immune cells, but they're made by those B lymphocytes. And they can go and find pathogens and bind to them and actually bring them to an innate cell to eat it or kill it. And that's sort of all what's shown here. T cells, on the other hand, are really designed to deal with intracellular infections. Because once a pathogen is inside of a cell, an antibody can't really find it. And that's shown here, perhaps if you have a virus inside of a cell. So there are ways that the immune system can know that the virus is inside. And basically our cells, when they get infected, become factories for these viruses. And what the immune system does is sacrifice the individual cell for the whole health of the organism. So if you kill the cell that has the virus, you're actually killing the factory for the virus and eliminating a lot of new potential viruses that might be made. So this is called a cytotoxic T cell because it's actually going to kill the infected cell as opposed to killing the pathogen individually, and that's what an antibody helps to do. Okay, so back to inherited and acquired defects in the immune system and what that could mean for susceptibility to infection. So, in order to understand that, you have to understand that the adaptive immune system, once it's activated, wants to always be turned on. It's aggressive, it really wants to fight the infection, so if you tell it to turn on, it actually doesn't really want to turn off. So a lot of what you're going to learn about with the immune response and the adaptive immune response is not only turning it off, or not only turning it on, but then turning it back off. So the response to an antigen, the normal response, is what the adaptive immune system always wants to do. It basically always wants to respond. So a deficient response would be that it is not responding. As you can imagine, though, sometimes you don't want a normal response. Sometimes you don't want the immune system turned on. For instance, here this says innocuous substance. That's like the food you eat. You do not want to turn on the immune response to the food you eat. So you actually don't want a normal response there. You would want a deficient response. So, if you have an infectious agent, you want your immune system turned on. If it does, you could have protective immunity. If the immune system doesn't get turned on, then you might have a recurrent or a persistent infection. But an innocuous substance is the opposite. You don't want the normal response. You don't want to have an allergy to peanuts or any of the food you eat. So you actually want the response to be deficient in that case. Now, a grafted organ, our immune systems really didn't evolve to deal with getting an organ from somebody else. So that's sort of an artificial system that we've been able to create and save lots of lives, but our immune system becomes a little bit of a problem, or a big problem with that. Our immune system is designed to reject and eliminate something that's foreign. So if you transplant in an organ from another person, it doesn't look just like you, and your immune system does what its job is, which is to eliminate that foreign thing, which would be to reject that organ. So we have to try to manipulate the immune system so that it doesn't reject it, and that's acceptance of that grafted organ. Now, self organs. Remember, I told you that our body's pretty good at eliminating adaptive immune cells that have receptors that can recognize self-antigens. But it's not 100%. So sometimes there are cells that can recognize self. We need to be able to turn those cells off. If we don't turn them off, you will get an autoimmune disease. But if we can turn them off, then we actually have tolerance to ourself, which is what is supposed to happen. Now, cancer is a little bit of a different story. Cancer cells start off as self cells, but then they mutate, of course, to become cancerous. So they don't look quite like self anymore. They change and do become foreign. And if our immune system can see that, then our immune system can actually eliminate a tumor. But of course, that doesn't happen all the time, and if our immune system cannot eliminate cancerous cells, then unfortunately you can get cancer. So the whole point of this table is to tell you that the normal response is to always respond. The adaptive immune response wants to be activated. And sometimes we want that, but sometimes we don't. And you'll learn throughout the lectures about all the ways that the immune response is actually controlled. Now again, I mentioned vaccination is one of the greatest benefits we've gotten from understanding immunology. And I'm just showing you a few examples here. You'll have a whole lecture later on about vaccines. But it shows you the dramatic effect of if we can get the adaptive immune system to make a memory response, but do it without you actually getting infected, then if you ever encounter that pathogen, that memory response protects you so you never get sick. So we've successfully done that with diphtheria, we've done it with polio, we've done it with measles, we've done it with smallpox, but there are still many other diseases out there that we would like to have vaccines for. So I want to spend the last few minutes sort of reviewing everything we talked about today with our broad overview of how the immune system works. So first, we have our anatomical barriers. They can be physical, remember, like your skin or the movement of the cilia in your lungs. You can have chemical barriers like the low pH in your stomach, or enzymes that are in things like saliva or tears that can break down some proteins. So that's your first barrier. If those anatomical barriers are breached or broken, then we have some complement and antimicrobial peptides. You'll learn about those in coming lectures. But those are basically some chemical compounds that also might be able to eliminate pathogens. And they're part of the innate immune response. But the really big part of the innate immune response is those innate immune cells, those myeloid cells. And you're going to learn about all those different types of myeloid cells. But their job is to be the sensor cells, the sentinels, at the sites of barriers, and if the barrier is breached, they're there and ready to respond to a threat if there's actually an infection with a pathogen. Now, if those innate immune cells cannot eliminate the infection on their own, they will recruit the adaptive immune response. And remember, that takes days to weeks to occur. So you could think about it another way. You have a pathogen that gets in. Maybe it's contained or eliminated by the barrier. So maybe you get something into your lungs, but your cilia move it and it comes back out. If that fails and you actually start to get an infection, then you have your innate immune cells that can recognize broad classes of pathogens and respond appropriately to kill them, to recruit other innate immune cells to kill them. And if that's enough, then the infection's eliminated locally. Maybe that happens in a cut on your skin, for instance. Now, if they can't eliminate that pathogen on their own, then they have to recruit effector cells. Initially, those might be effector cells of the innate immune system. So they're a little bit more specialized in how they can work, but they're not pathogen specific yet. They're still part of that early, quick and dirty response. But that can take a few days to happen. Now, if those cells can't eliminate the infection, then those innate immune cells travel to lymphoid organs where they can find cells of the adaptive immune system and alert them that there's a big problem that they can't eliminate on their own, and that adaptive immune response has to get generated and then go to the site of infection and eliminate the infection. So this is the anatomy of an immune response all in one slide. And we're going to spend the next 28 lectures breaking this down. But overall, you can see that you've got an intact barrier over here. You've got some bacteria on the surface. Pathogenic bacteria, not commensals. If you have a break in that barrier, those bacteria get in. They're your sentinel sensing cells, your innate immune cells that are there waiting just for this type of situation. So you can see that they will start to eat and kill some of those invading pathogens. But then some of those cells are going to take that pathogen. They're going to travel through the bloodstream to lymphoid organs. They're going to interact with cells of the adaptive immune system. They're basically saying, hey, look what I found. We have to mount a stronger response to this. I need your help. The adaptive immune response gets activated in a lymphoid organ, and then cells from that activation, those clones, which occur in the adaptive immune cells, travel back to the site of infection and eventually eliminate the infection completely. One other thing to show here is that once you have the breach, for instance, you have a cut in your skin, of course it has to seal over, and the innate immune system actually helps in wound healing as well as eliminating pathogens. So, to summarize what we talked about today, the immune system comprises cells and soluble factors. And remember, those soluble factors mostly come in the form of a chemokine, which tells an immune cell where to go, and a cytokine, which recruits specific types of cells and tells those cells what to do. The immune system has two main functional arms, the innate and the adaptive. The innate response, you're born with it. It always occurs first. And components of the innate response are always found at barrier sites in your body. They're positioned where there's most likely to be a breach and where a pathogen is most likely to enter your body. The adaptive response must be initiated by the innate immune response. And that doesn't usually ever occur at the site of infection. It occurs in a lymphoid organ, and you'll learn more about specific lymphoid organ in the next lecture. The innate response is always going to be less specific than the adaptive response, but it's always going to be much faster than the adaptive response. Memory responses. So your body remembers that you had an infection before and helps you fight it off so you don't get sick the second time. That almost only ever happens with the adaptive immune response. So memory is really associated with the adaptive immune response. Those myeloid cells that you have at barrier sites, they sort of do the same thing every time there's an infection. Even if it's an infection you've had before, they don't necessarily remember that and respond differently. Also remember, the adaptive immune response default is that once it's activated, it wants to just be on and do its job. And sometimes that's a good thing, but sometimes we don't really want that adaptive immune response turned on. Or even if it is turned on during infection, we do have to have a way of turning it off. Imagine that you get strep throat and your tonsils get huge. Your tonsils are lymph nodes, and those are immune cells there trying to fight the infection. But once the infection's gone, you don't want your tonsils to stay huge. The immune response always has to have a way of being turned off. Now, the innate response inherently just sort of goes off after a few days. It doesn't usually stay perpetually activated. But it's the adaptive immune response where we really have to have lots of controls. And you'll learn about those. So, I wanted to conclude by giving you some hints about how to learn immunology. Because a lot of people think that learning immunology is difficult. They equate it to learning a new language. You are going to learn about a lot of different cell types and a lot of different molecules. And it doesn't work well to just memorize all of those names because there's too many. So you really have to try to think logically about what you want your immune system to do. Again, think about, you've got barrier sites. If a barrier's breached, what's the first thing that should happen? How do you want your immune response to proceed? If you think logically about how you would fight off an infection, then it's easier to remember those cell names and all of those molecules that you're going to hear about throughout the lecture series. So learn the processes first, and then go back and try to remember all of the names of the cells, not the other way around. And remember, when you're trying to think logically and learn the processes, try to think about, is it why we have an immune system or what it does? Because that's going to help you understand and learn better how the immune system actually works. Again, welcome to the Immunology Lecture Series. I hope you enjoy the next 28 lectures. And remember to always have your textbook with you so you can look at the figures in the book as you watch the lectures. And again, make sure you view those lectures in order. Thank you.